Hello everyone and welcome to this new video about abstract algebra. Today we're going to talk about isomorphisms and homomorphisms of groups. So let's start by defining what these things are. We won't start from a technical abstract definition, but we will start by introducing a little bit of the motivation behind these ideas. So if you're watching these videos, you're probably already familiar with discrete math and some naive set theory. By naive set theory, I mean set theory without worrying too much about all the axiomatic structure, about Zermelo-Fraenkel axioms, all these things. Just, set theory in a very easy way. So, and you probably know that when we work with sets, at a certain point we start asking, we start questioning about how many elements are there in a set, and when are two sets equals in terms of just their set structure. And well, the answer we come up with is that two sets, A and B, are equal, so we can write A is equal to B, if we can construct a map F from A to B, such that this map is injective and surjective, so it's a bijection. And here I've denoted it with this arrow like this, where this denotes a bijection, but if it's not clear, I can just specify it up here as well. And so, why do we say this? Because if we construct a bijection, what this means that A and B have the same number of elements. But if we consider A and B as mathematical structures with just with their structure of sets, then of course we can treat them as equal sets if they just have the same cardinality. And now we wish to ask the same question, but this time with sets together with an operation, and this operation should satisfy the group axioms. So we're now interested in groups. So our question is, when are groups equal? So when can we treat two groups as the same, basically? And well, we see that we cannot just say that two groups are the same when they have the same order, because let's expand on this. For example, let's consider two groups of the same order. For example, the symmetries of a equilateral triangle that is the dihedral group of order 6. And let's, for example, consider Z6, which is the additive group of integers mod 6. Both of them have order 6. But you can actually just understand it a little bit yourself. I'm going to show that, well, the way in which we combine elements with their operations are radically different. So, of course, as sets, let's call D3 basically, and let's just say that is equal to ER squared, then S and RS. So, and R squared S. So it is basically a set of 6 elements. Okay, and of course, well, we can construct a bijection between these sets. We can map, for example, E to 0, so the identity rotation to the additive identity of Z6, and then R to 1, for example, R squared to 2, and so on. So we can construct a set bijection. But now let's consider something. And so let's schematically view these groups more geometrically. So let's suppose that our elements are points, like this, and that their combination relations, this means that summing one with another, actually I think it is even better if we visualize it with a Kelly table. So let's draw a Kelly table for Z6. And this is the Kelly table for Z6. And now let's write a Kelly table for D3 here on the right. And here we go. So just note that the other reflections not as RS, R squared S, but just as A, S, B, and C to basically represent the rotation that rotates, the reflection that reflects that around the vertex A, B, and C respectively. And now I want you to focus the attention on something. So the bijection we constructed was that, for example, we mapped R squared to 2. Okay, but now, for example, let's compare these Cayley tables. Let's see that 2, which we could see as, like the image of this map that we constructed, the image of R squared under this map. Well, if we consider 2 and we, for example, combine it with 2, then what we get is 4. So 2 plus 2, which is of f of r squared plus f of r squared, is equal to 4. But 4 here gets mapped to s, so this is f of s. But let's see here, if I combine r squared and r squared inside of this other group, let's see here, if I combine r squared and r squared, we get r, but f of r is 1. And we notice that now, well, we get that basically, in other words, this map that we constructed, even though it is a bijection, so it provides an equality for the underlying set structure of our group, it cannot provide an algebraic equality because the operation is not preserved, as you can see here. So we need to also require that in order for two groups to be equal, their algebraic group structure, of course, because of course we can also consider more sophisticated groups, and when you will study more complex algebraic structures, you will see that, and we will consider different notions of isomorphisms. But here we're just concerned with groups, and now for groups we want an isomorphism, which is a map that should provide equality to preserve the group operation. In this case it doesn't, so this is not an isomorphism. Actually, let's just dive a little bit deeper on the notion of isomorphism. Isomorphism comes from the Greek word isos and morphos, which basically means the same shape. And so now it should be clear why we call such things an isomorphism. And so now we're ready to define an isomorphism. So we're going to give a definition. And this is the notion of an isomorphism. We call a function that goes from a group to another group, G to G tilde, an isomorphism if and only if phi is bijective. This means that it's a surjective and one-to-one function. And furthermore, if it preserves the group operation. This means that phi of a times b has to be equal to phi of a times phi of b. Now notice here that the operation that we're considering here, this is the operation of g. But this operation here, this is the operation of g prime. So as you can see, what we basically require is that the operation is preserved. This means that if you have two elements in the original group, so we can call them alpha and beta, well, if we combine them here in another element that we can call gamma, well then what we want is that in our group G tilde, which is our image group, and let's suppose that alpha gets mapped to phi of alpha, and maybe beta gets mapped to phi of beta, okay, well then what we want is that if we now combine these other two groups under the operation, this is the operation of, we could say, operation of G, okay, and here we're combining them under the operation of G tilde. So if we combine them under the operation of G tilde, and we can call this, this is basically equal to phi alpha times phi beta, we can call this gamma tilde, and let's also specify here that this is alpha times beta. Well then, what we want is that if we map this under phi, we go here. This is basically what an isomorphism is, more graphically. So this is what we're asking. Furthermore, we don't just want that it preserves the group operation, we also want it to be bijective. Because if that was not the case, then we would have the notion of a homomorphism. So, which again means from Greek similar structure. And an homomorphism is just a function G, function from a group G to another group G tilde, such that for all A, B, and G, it preserves the group operation. So we have this. This is an homomorphism. So now that we have the notion of isomorphisms and homomorphisms, let's go and give some examples. So let's start with this example here, example 1. And this example is actually, we say, a little bit analytical. We're gonna draw some inspiration from real analysis. What we want to show is that, so we're considering the group G to be the group of positive real numbers under multiplication, and And our group G tilde will be the group of all real numbers under addition. What we want to show is that phi of x, given by the natural logarithm of x, is a group isomorphism, provides an isomorphism between those groups. And by the way, I forgot to mention another definition. If there exists an isomorphism between two groups, so if there exists phi between G and G tilde isomorphism, then we're gonna say that G and G tilde are isomorphic, and we're gonna write it like this. This basically means that they're algebraically the same. So let's go back to the example. Let's actually prove it. So the first thing which we want to prove is that the natural logarithm is a bijection. So meaning that taking the natural logarithm function from the positive real numbers to the real numbers, it is both surjective and one-to-one. So we're gonna first check surjectivity. So suppose we have a y in R. We basically ask ourselves, does there exist an x in the positive real numbers such that the natural logarithm of x is equal to y? And well, that x exists and it's equal to e to the y, and it is a positive. It is a positive real numbers by the nature of the exponential, which is a function with the graph like this. And so we have that it is a surjective function. It is also an injective function. That's because it is a strictly increasing function. And well, here we're using some facts from analysis, but I'm sure you won't complain if we just skip some details about our proof here, because of course this is a video series about algebra, and let's not lose the focus on the algebraic structures that we're studying. But so again, this we could say sketch of a proof of why, of course, the natural logarithm in this case is a bijection. It's not super rigorous, super in-depth, but again, here we're not studying analysis, we're studying groups. So with this said, so we've now shown that natural logarithm of x in this case is bijective. Now let's see that it is a homomorphism, so that preserves the group structure. So let's consider natural logarithm of x times y, where x and y are elements of this group G. And well, by the properties of the natural logarithm, this is equal to natural logarithm of x plus the natural logarithm of y, which is just equal to, and we basically reached the condition that we wanted, because this is literally this condition here that we wanted to show. And so it follows that these two groups are isomorphic. And the natural logarithm of x is the function that constructs this isomorphism. Now, moving to another example. And now we're going to still consider our groups from before, but we're going to consider a function this time that goes from G tilde to G. In other words, a function from the additive group of real numbers to the multiplicative group of positive real numbers. This function that we're going to consider is the exponential function, and what we want to show is that this is an isomorphism, meaning that in other words, this function is bijective and this function is an isomorphism. So again, here the bijectivity comes from the what are known properties of this function in real analysis. So where, of course, since it is a strictly increasing function and its image is the positive real numbers, so having as an image the positive real numbers, this implies that it's surjective with respect to these sets that we're taking, and of course being strictly increasing throughout all of its domain implies that it is an injective function. And so from this it follows the bijectivity really quick. And from, on the other hand, from the other properties that it possesses, since we know that given x and y in the real numbers, e to the x plus y is equal to e to the x times e to the y, well, this is, on the other hand, the proof that the exponential is a homomorphism. From this it follows that it is an isomorphism, as we wanted to show. Now let's give a counterexample. So let's give an example of a function which is not an isomorphism. And here we're going to take as an example the additive group of real numbers, and we're going to define our function to be x cubed. So it is clear why this function is not an isomorphism. That is because even though the function is bijective, as you can see, because its graph is something like this, so it is bijective, but it is not a homomorphism, meaning that it does not preserve the group structure. So if we have, for example, x and y in R, then of course we know that in general x plus y cubed is not equal to x cubed plus y cubed in general. And so from this fact it follows that our function phi is not an isomorphism of groups. Now let's provide another pretty interesting example. Actually, we're not going to mark it as an example, we're going to mark it as a fact because it's a pretty important result, and that is that any infinite cyclic group is isomorphic to the integers, to the additive group of the integers. And so let's prove this. This is not too difficult because the construction of an isomorphism is pretty straightforward. So let's suppose that G is an infinite cyclic group, and let's suppose that the generator of this group is A. In other words, this can be written as a to the k, where k is an integer. Now, the first thing that we want to show is that we can construct a function phi from this group to the additive group of the integers, such that this is bijective and a homomorphism. So let's first show that this is bijective, and this follows pretty easily because suppose that we have, for example, m in the, and first let's define a function, of course. And so we're going to define a function to be mapping an element a to the L, because of course we know that since G is an infinite cyclic group generated by A, then all elements of A of G will be of the form a to the L for an integer L. And what we're going to say is that this function is going to map A to the L to just L in the integers. So the first point, which is surjectivity, we're going to suppose that m is an integer. Well, then there exists a to the m inside of G, such that phi of a to the m is equal to m. And so we've shown that this is surjective. For injectivity, on the other hand, we're going to suppose that there exists, for example, L and L tilde, such that phi of a to the L is equal to phi of a to the L tilde. I'm going to call this big L. Okay, but actually for a theorem that we proved a lot of videos ago, but we're not going to go to it because it's very it was basically in the videos about the cyclic groups. It basically assures that they're equal, because basically you had that if an element at infinite order, for example if an element A at an infinite order, then a to the m would be equal to a to the m tilde if and only if m was equal to m tilde. And so using this fact we can basically prove this and show that actually this mapping is not only injective, it is also well defined. And so from this it functions that is a bijective function. From this it follows that it is a bijective function. And for the homomorphism part, so for the preservation of the group operation, all we have to do is show that if we take phi of a to the k times a to the L, then this is equal to k plus L. But this follows from the definitions of the operation, and basically of which our infinite cyclic group is furnished. And so we have basically shown that any infinite cyclic group is isomorphic to the additive group of integers. So we're going to conclude this video with a last example, and this involves groups of matrices. So we're going to consider an example regarding groups of matrices, and that is we're going to consider SL2R, so the group of 2 by 2 matrices with determinant 1. If you recall, this is the definition of SL2. And of course real entries, so I'm going to specify that. And now what we want to show is that the application is that the function given by phi of A is equal to, actually let's use as a subscript the matrix. We're going to take the conjugation by. You probably recall this if you ever took a course in linear algebra. This is the conjugation by a matrix operation. And what we want to show is that this is an isomorphism. So we're going to start by showing that phi of B is a bijection. And how can we do that? Well, we start by well-definedness and injectivity. So suppose that we have two matrices, A and A tilde in SL2R. Well, then we have that phi of B is equal to phi of A tilde if and only if A is equal to A tilde by the algebraic properties of matrices, namely by right and left cancellation. So from this we get this if and only if relationship. And for surjectivity, so suppose we have a matrix, for example, C in SL2R. Well, then there exists a matrix D in SL2R such that phi of B of D is equal to C. And this matrix D is in particular equal to B to the minus 1 and then CB. Let's see why that works, because if we take phi of B of D, then this is B times B to the minus 1 times C times B to the minus 1, but these two are just the identity. This reduces to C, and so this works out. So now for the and also let's show that it is actually that the image, okay, of a matrix under this conjugation is actually in the special linear group of order 2, of a special linear group of 2 by 2 matrices, of 2 by 2 real matrices. And well, what assures us that this is actually the case is that if we take the determinant of this, by the properties of the determinant, this is equal to the determinant of B times the determinant of B to the minus 1 times the determinant of A. And again, by the properties of the determinant, and since all these determinants are all equal to 1, we get that this is equal to 1. And so phi of B of A is in SL2R. So with this we have shown that we could say the images of elements of SL2R under this function are still inside SL2R. Not only that, but this is also a bijective function. Now all we have to show is that it preserves multiplication of matrices. So it is an isomorphism basically. And so to do that, let's pick for example C and D inside of SL2R. Let's consider phi of B of C times D. Well, what is that? That is just equal to B times C times D times B to the minus 1, right? Okay, but what if we sandwich inside C and D B to the minus 1 and then B again, and then using associativity and algebraic properties of matrices, what we get is that we get B times C times B to the minus 1 times B times D times B to the minus 1, but it's just phi of B of C times phi of B of D. And comparing the right and the left hand side of these equations completes our proof of this mini fact. And so with this said, I think we have provided enough examples of isomorphisms and homomorphisms in this video, and in the next one we will start proving some more abstract results, more general results about isomorphisms of groups.